Good morning, and welcome to the ATCO SpaceLab Speaker Series. Thank you for joining us today. My name is Kelsey Stephen, and I'm a member of ATCO's Transformation Team. I'm pleased to be your moderator today. I acknowledge the Indigenous peoples that are traditional custodians of the lands that we are on today. While this is a virtual platform, I will take a moment to reflect on the meaning of place, and in doing so recognize the various traditional, ancestral, and unceded lands on which we do our business. I do this to reaffirm my commitment and responsibility in improving relationships between nations and to improving my own understanding of local Indigenous peoples and their cultures. Today's lecture is a one-way video and audio format. Please ask questions by using the Q&A button at the top of your screen, and we will answer these questions at the end of the lecture. We are honored to be joined by Dr. Greg Pavliotis, a professor of applied mathematics and director of the CNRS Imperial Abraham de Moivre International Research Laboratory at Imperial College London. He has published more than 120 scientific papers, and his work has been cited more than 7,200 times. Professor Pavliotis has taught and presented his work internationally and has held visiting professorships at various institutions across Europe. Today's lecture explores how mathematical models of human interaction help us understand group behavior in the social sciences. Professor Pavliotis will share what multi-agent models reveal about consensus and other collective behaviors that can emerge within groups. He will address the impact of this emergence on the clustering and stability of the group dynamics. He will also present methods of using data to improve the interaction models and discuss strategies for steering groups towards desired behavioral outcomes. We are excited to welcome an expert of Professor Pavliotis' caliber, and we eagerly anticipate this enlightening session. Dr. Pavliotis, the floor is yours.
Great. So thank you so much for the invitation. So this is great, and it's very nice to also meet with all of you, and I hope you will find this presentation useful and interesting. So let me share my screen. Okay, great. All right, so I'll start with an experiment, and then I'll tell you what this is about. So this is the type of agent-based model that we're thinking of. So you have a group of individuals that they start interacting. Now the details of the actual interaction law are not necessarily important at this moment. And then they quite often form clusters. Okay, so you can think of it as a very sort of simple toy model for polarization. These clusters can persist over very long time intervals, and as you can see, they actually merge. They can merge, so they can they interact once they have formed, and then they can lead to the formation of a single cluster that can be interpreted in the sense of opinion formation or reaching consensus. So again, I will have some kind of movies that I will be maybe will show more than once during the talk. Let me show you one more movie, and then I'll start with the maths. So again, so this is kind of again, it's I'm not going to get into the details of the parameters and so on. Please feel free to or to ask questions during the talk, or I can discuss about we can discuss about the details later. But again, so you have now a system of agents that interact via an interaction law that is quite similar to the so-called bounded confidence model from opinion dynamics, which is one of the models that I will consider in some detail during the presentation. And now I start again. I start finding the model. So the clusters form. Okay, again, you can think of this as a very kind of simple toy model for polarization. And now they persist. So they can they stay. They persist over very long time intervals. And depending again on the parameters of the interaction strength and so on, they can eventually merge and lead to a single cluster that again we can interpret in terms of cluster formation, of consensus formation. And as you can see, this process can be very, very slow. Okay, it can take a very long time for consensus to form. Okay, I will come back to this. So just to confirm, so can you all see me and hear me? Is because sorry, at the moment, yeah, okay. Sorry, yeah, okay. Just it's fine. Okay, sorry. Thank you for this. Thank you for confirming. Okay, so the title then is Interactive Multi-Agent Models in the Social Sciences. Now, again, I should sort of confess that really my training is in mathematical physics and also applied mathematics. So most of the talk will actually be quite technical, but I still hope you will interesting. I should also warn you that yeah, the internet connection on my side is not great, so there might be some interruptions. Hopefully, we'll be fine. Okay, so first, in terms of mathematical models, I will be looking at agent-based models that are given in the form of a diffusion process, so of interacting diffusions. So again, maybe you remember some of or you recognize rather some of the symbols from your statistical physics courses or from your mathematics courses. So I have a system of agents, or I will be using the term particles quite often, that interact via an interaction kernel W. And they also live in a noisy environment. So I have noise that acts directly on the agents. Okay, here for simplicity, I will model the noise that, if you like, it can describe uncertainty in the model, it can describe environmental noise and so on, in the simplest possible form, which is that of Brownian motion. Okay, so it's a sort of a white noise, space-time white noise, as we would call we will call it in physics. Okay, now I want to consider the large population limit. So, and sorry, we keep getting. Let me sorry. Let me see if I can. Can you hear me? Can you still hear me? Yes. Yeah. Thank you. Thank you. All right. So this is the model that I consider. So and then I want to consider the large population limit. So I will send n to infinity. So this is, of course, you will tell me we don't have infinitely many agents, but this is a useful mathematical idealization because then it will lead to a mathematical model that is much simpler to analyze. Okay, so if I send n to infinity and then I obtain a type of stochastic differential equation called a Makin as this. So Makin was a famous mathematician that worked at New York University. And then so this equation describes the position of the agent, of the average agent in the limit as the number of agents goes to infinity, and its distribution function, so the probability of finding the agent in a certain area of state space, is governed by this partial differential equation, which is the so-called Makin-Vlasov PDE. So in terms of the mathematical model, so the sort of the main sort of equation that I will study in order to describe things like synchronization, consensus formation, and so on, is this PDE model. Okay, okay, there are many recent papers. There's something I've been working on for quite some time now. Now, in terms of direct connection to models in the social sciences, in particular to models for opinion formation and consensus formation. Maybe this recent paper might be of some interest, so approximating particle-based clustering dynamics by stochastic PDEs. I will discuss about how clusters form, and then I will discuss about how to actually control them. Okay, so the last thing that I will tell you is how, in principle, one could use tools from optimal control theory in order to control the dynamics, and if you like, to steer the dynamics towards a sort of preferred consensus state. There is quite a bit of work on learning interaction kernels from data, and I will give you an overview of some of these results. And one can also develop machine learning-based methods for actually learning multi-agent models from data. And one can do this for systems like, for example, the Harris-Wilson model for the dynamics of urban environments, or you can do this for the UK power grid. So there are lots of interesting applications that I will not actually have time to discuss about today. And then there is a lot of more sort of rigorous analysis on that I will maybe skip. Yeah, I will skip lots of slides because some of the stuff is actually quite technical and I don't want to bore you with technical details. So the sort of prototype or paradigm of the type of agent-based model and the type of collective behavior that we're interested in is the so-called Kuramoto model, or maybe a more accurate description of this is the so-called noisy Kuramoto model. So you have here a bands of nonlinear oscillators. Okay, so the interaction kernel, if you like, is just the sign moving on the circle. You have the structure and the scaling that I described before. So it's a 1 over n. So it's weakly interacting agents in the sense that the strength of the interaction scales like 1 over the number of agents. This is the correct scaling that leads to a sort of a well-defined thermodynamic limit. Again, I'm happy to tell you more about this. There is a parameter kappa here that controls the interaction strength. And this is white noise. Now, again, so since, as I mentioned, my training is in statistical mechanics, I always denote the strength of the noise as the square root of 2 beta inverse. And beta is the so-called inverse temperature. But again, if you prefer, just, you can call this whole thing like just sigma. Okay, and now 2 different stable configurations can emerge. So you run these dynamics, and then if the interaction strength is weak. So if the strength with which the oscillators or the agents interact is not very large, then noise wins. And in the end, you end up with a uniform distribution of frequencies, which is described as no phase locking. And this is kind of the disordered state. There is no order in this state. If you like, is the state that maximizes the entropy. On the other hand, if the interaction between the agents measured by this parameter kappa is sufficiently strong, then the agents can actually sort of coordinate themselves or synchronize themselves, and we end up with this ordered state in which all agents end up with the same frequency. Okay, so this is the so-called phase locking. And now the main sort of approach that I will take in this example, and also this example, the bounded confidence model for opinion formation, is that I will think of this as a phase transition in the sense of statistical physics. Okay, so I will think of this as a transition between a disordered state. So you can think of a gas, I guess, to an ordered state. Okay. And so the emergence of collective behavior at large scales will be interpreted as a disorder-order phase transition. Okay, so this is the main observation, if you like, or the main sort of theme around which this research program has developed. Okay, now again, if I do indeed interpret this as a phase transition, so then this is a so-called second order phase transition, and it corresponds to a so-called Pittsburgh bifurcation. So at sufficiently low interaction strengths, the uniform distribution corresponding to this disordered state is stable, and then at a sufficiently large, at an appropriate interaction strength, I have what we would call in physics symmetry breaking, and then the disordered state becomes unstable. So you should there should have been dots here, so denoting this is an unstable steady state, and then this new synchronized state emerges that corresponds to a single cluster. Okay, this is this localized distribution. So all agents have the same frequency. And this is a single cluster state. Now, let me go back to one of the one of the movies that I showed you. So this would correspond to the case where actually a single cluster forms eventually. So again, let me show you yet another numerical experiment. So I have my agents interacting, they're doing their thing, and then eventually I end up with a single cluster. Okay, so these two are due to the boundary conditions. I don't want to get into this, but you can ignore them. So it's basically this cluster state corresponding to this so-called von Mises distribution. Okay, so then one of the sort of purposes of this research is to provide a rigorous justification for the fact that you do indeed have this phase transition and to link it to clustering phenomena and so on. And we will also then want to infer the interaction law from data. And then we will want to control the interactions, okay? We will want to apply optimal control methodologies so that we can steer the dynamics towards a pre-chosen clustered state. Okay, now, again, as I mentioned, I will skip almost all of the mathematical details, but again, just to make the link with statistical mechanics and with the theory of phase transitions, I have a free energy for this problem. So, and then this is given in terms of this entropic term. So this is the entropy that you might recognize from your physics course, plus an interaction energy, and then I can also have an internal energy, but let's ignore this for the time being. So I have entropy. Again, now whether you call this minus the entropy or the actual entropy depends. So in the mathematics and physics literatures, the entropy differs by a minus sign. And then you have the interaction energy here. And you can precisely define what a transition point is. So if I go back to my to the Kuramoto model, I can define precisely what it means to have a transition point, which means that up to here, the uniform distribution corresponding to the disordered state is the unique minimizer of this free energy. So it's a stable stationary state. Here at this point, the two phases coexist. And above this, then the uniform distribution becomes unstable, and the localized state described by this single cluster becomes the unique minimizer of the free energy. Again, there is a sort of, it's a purely, if you like, thermodynamic definition of phase transitions, and it is very kind of convenient for and useful for this for the problem at hand. Okay, again, please do interrupt me if there are any questions or if there are any points that need to be clarified. Okay, so now maybe I should also now view full screen audio. Yeah, okay. So now the second thing that we need, and you will see that this actually is quite crucial, is to distinguish between first order and second order phase transitions. Again, in physics, we learned that they can be first order or second order phase transitions. Here we need a slightly different terminology. So we will refer to continuous and discontinuous phase transitions. Again, I won't give any details, but the point is that whether we have a jump here from one stationary state to another, or whether, as it is the case here, we have a continuous a transformation from this stationary state, the uniform one, to the order one, this corresponds to a discontinuous and a continuous phase transition. Okay, so this is an example of a second order or continuous phase transition. Okay, so the notion of transition points and of phase transitions is, of course, very much related to stability. So if I go back to my figure here, the uniform the disordered state is stable up to here, and then it becomes unstable, and then the new branch emerges. Okay, so this point where I have this transition between one state and another is also the point where the disordered state becomes unstable, and therefore I can no longer observe it. Now, there are again lots of technical details because there can be differences between transition points, bifurcation points, and points of linear stability. But very roughly speaking, this is the idea. So I have a transition from one state to another, so from the disordered state to the ordered state, at the point where the ordered state, the disordered state, so the uniform distribution, is no longer stable. Okay, so now there is actually a quite sort of detailed characterization of phase transitions for this type of problems. Some of it goes back to kind of people like Oliver Penrose. You might have heard of Roger Penrose, who got the Nobel Prize in physics a few years ago. So Oliver Penrose is his brother. Where we can characterize under what conditions the free energy can have a transition point and properties of transitions. The one point that I will mention here that is worth keeping in mind is that in dimensions higher than 1, discontinuous phase transitions are generic. Okay, again, I can make this much more precise if anyone is interested, but as you will see soon, so the formation of clusters is actually related to the presence of discontinuous phase transitions, which turn out to be generic in dimensions higher than 1. Okay. Now, so there is a very general theorem. Anyway, there is a quite general characterization of the type of interaction kernels that can lead to continuous and discontinuous phase transitions. And this was published a few years ago in the Archive for Rational Mechanics and Analysis. I consider the problem now on the torus with periodic boundary conditions. So this means that I can basically expand everything into a Fourier series. Okay, so the my Kim-Vlasov PD that I wrote here, and you can ignore this term V, is posed on the unit torus, so on a circle, if you like, or the surface of the sphere with periodic boundary conditions, and the interaction kernel can be written as a cosine Fourier series because it has to be symmetric, and similarly I can expand the solution to the PD in a Fourier series. And then I have a criterion that tells me when I can expect to have phase transitions and whether they're continuous or discontinuous. So maybe it's better to just look at this graphic description of the theorem here. So if I take the Fourier transform of my interaction kernel, as long as it has negative Fourier modes, then there will be non-uniqueness of stationary states. So the formation of clusters, and in particular the emergence of collective behavior at sufficiently high interaction strengths, will happen as long as the interaction kernel has negative Fourier modes. Second, if there is a dominant negative Fourier mode for the interaction kernel, then I will have a continuous phase transition. Again, think of this Kuramoto model for synchronization where there's only a single negative Fourier mode, so the interaction potential is minus cosine x. So for all types of interacting particle systems that look like Kuramoto, I will have a continuous phase transition, so a second order phase transition. On the other hand, if I have many non-zero Fourier modes that compete with each other, and again, I can make it very precise in terms of a resonance condition. But again, think of this picture. So here is the Fourier transform of the interaction kernel. So if I have several negative Fourier modes, and then if this resonance condition is satisfied, then I will have a second order phase transition. Now, again, and without getting into details, I mentioned here that I made this kind of, if you like, cryptic remark that in dimensions higher than 1, discontinuous phase transitions are generic. And maybe you can see the link between this statement and the fact that you have this resonance condition that needs to be satisfied, because of course resonance conditions, it's much easier for them to be satisfied in higher dimensions. Okay, it's much easier to find wave numbers where a condition like this is satisfied. Okay, so now in particular, a corollary to this theorem is that if my interaction is localized, yeah, sorry, so we were interrupted. So if my interaction potential is localized, and again, think of the bounded confidence model from opinion dynamics that I will show again in a second if you haven't seen it before. And if they're attractive, then I will end up with these continuous phase transitions. Now, since I'm in a box, so I have periodic boundary conditions and I'm in an enclosed box, then for repulsive interactions, of course, this means that the uniform distribution is always positive. So only the disordered state exists as a stationary state. So I definitely need to have attraction between the agents, and I need the interaction to be sufficiently localized so that I can have the emergence of clusters. Okay, I will skip this. Okay, so then using this sort of general theorem, we can prove that it is indeed the case that for the Kuramoto model, we have a second order phase transition. And in fact, here it's a generalization an extension of the result where we take an interaction kernel to be of the form minus cosine of kx, where k is the kth harmonic. And then not only do we have a continuous phase transition for this model, but in the limit as the interaction strength goes to infinity, this converges to the sum of k clusters. Okay, so we can also characterize the number of clusters that we end up with. And okay, I skip this. Sorry. Yeah, okay, so I leave this for the time being. Okay, maybe very briefly, you can also study, no, actually, no, let's leave it. So you can study the fluctuations around this mean field limit, and the fluctuations actually play a quite important role, both in terms of the dynamics of the system, as well as when developing inference methodologies. So you can characterize completely the fluctuations around this mean field description that you obtain in the limit as n goes to infinity, but I'll leave this for the time being. Now I will discuss about this bounded confidence model. So I have a system of interacting agents moving. So now I consider my opinion space to be 0, 1. If you like, you can think of 0 as being whatever extreme left and 1 extreme right, though there's no analogy with whatever real politics and so on. I'm not gonna make any analogies whatsoever in connection to this, but you can think of this. So one extreme opinion is at the left end point, the other extreme opinion is at the right end point. I don't have any structure in space, so this is only opinion space, okay? And now my agents interact via this so-called bounded confidence model or Hagselmann-Krause model. And the idea is the following. So there is this so-called influence function here, phi of theta, that is something that is very localized. So it's basically like we interact with agents so its agent interacts with other agents in their neighborhood in opinion space. Okay, so we interact with agents that are close to us in opinion, in terms so that they share similar opinions to us, and then we adopt some sort of an average opinion in the neighborhood. So there is this influence function, and it is parameterized by the so-called influence kernel. Okay, so R tells us how this parameter actually, sorry, theta 2, I apologize, theta 2 tells us how large our neighborhood is in opinion space. So with how many agents, if you like, an individual agent interact in terms of how far the opinions of the other agents are from the agent. So again, this is precisely of the form of a system of interacting diffusions for which this theory that I'm presenting here actually applies. We can pass to the mean field limit. We can consider the effect of different boundary conditions, so different behavior at close to the two extremes. We can add leaders, we can add extreme groups, so this model is actually quite versatile. But I want to show you some experiments. So here are the typical sort of configurations, if you like, that we can get. So I plot here several trajectories of my agents. So starting at time t equals 0, and we can start assuming that the opinions of individuals at time t equals 0 are uniformly distributed, say. Then they evolve in time. And now, if the interaction between the agents is not sufficiently strong, then there is no consensus. So this corresponds to the disordered state in the Kuramoto model, so in model for synchronization. Okay. Now, as I start increasing the interaction strength, but also increasing the radius in opinion space in which agents interact, then clusters form. Okay, so these clusters are precisely, maybe I can, well, I'll show you a movie again in a second. So clusters form. Now, I keep increasing the interaction strength, and now you can see that fewer clusters and sort of bigger clusters form. They interact with each other, and eventually I have the formation of a single cluster that this corresponds to consensus formation. So again, consensus formation for this type of models is the equivalent of this phase locking mechanism for Kuramoto type models, and it means that eventually all agents converge to the same opinion. Okay, so they have the same opinion. It's quite sorry. Yeah. So let me show you another movie where we simulate exactly this model. Leave this. I leave this. So yeah, so it's this. Okay, so I simulate this bounded confidence model, and then I use a clustering algorithm in order to learn the clusters from data. Okay, I will have more to say about this in a few minutes about inference methodologies, but basically this is what we do here. So you see now, so we see the trajectories, we see clusters forming, okay? And then, and you can see, so now there are two clusters that have already formed here. They coalesce and they form a new, or they merge and they form a new cluster and so on. And this goes on until a single cluster has formed. So the mechanism in this model for sort of reaching consensus is via the formation of, I guess, polarized states that then interact with each other. So, well, clusters that interact with each other until they finally we end up with a single cluster. Okay, so now for this type of model, we can prove rigorously that a first-order phase transition occurs. So it has a discontinuous phase transition, and now the point is that so for systems that exhibit discontinuous phase transitions, they are characterized by the formation of this kind of clusters that persist over very long time intervals. So this is what, again, in physics is quite often called dynamical metastability. So the fact that clusters form and that they are stable over very long time intervals is directly linked to the fact that we have a discontinuous phase transition. Now, many of these results and of this type of models can be also extended to dynamics on random graphs. Now, if we're interested in modeling in sort of mathematical models in the social sciences, then clearly we need to take into account the underlying network structure, and this can be done. There are many works that study sort of interacting particle systems on graphs at the moment. I show you here one numerical experiment done with jointly with a current PhD student, Benedetta Bertolli, and also a former PhD student, Nico Zagli, where we study the formation of clusters for similar types of interactions, of interaction laws, but on random graphs. So you can think of like small world graphs, you can think of Rene graphs, all sorts of different things, and you can see that how the clusters form, and they eventually merge, so they interact, so that in the end a single cluster corresponding to opinion information becomes dominant. Again, there are lots of things that still need to be understood in this problem, and so the phenomenology, if you like, of interacting particle systems on graphs and so on is actually very interesting. Again, we can discuss more about it after the end of my talk. Okay, now let me discuss briefly the sort of some results in connection to like this the rigorous justification to the fact that we have cluster formation and that then clusters interact. So this is done work with Andres Lichting, who is in Ulm in Germany, Nico Gerber, who is a student of Andrew in Ulm, and Rizal Palani, who is my former PhD student, and now he's at ETH in Zurich. Again, I don't know how much I should tell you, but let me well, let's briefly discuss. So I take so this is this Hagselmann-Krause model. It's what we discussed, that people agents interact with other agents in their neighborhood in opinion space, and the size of the neighborhood is modeled by the size of this domain here. So I have one parameter, which here I denote by gamma, which is the interaction strength. I have another parameter, which is the characteristic length scale of the interaction. So this is the influence radius. And I want to find an appropriate scaling limit that involves both gamma and L, so that I can show that in this appropriate scaling limit, the interacting particle system converges to the dynamics of these clusters that form. And eventually the clusters interact with each other so that a unique cluster forms. Okay, so if you like, there are two aspects of this. So first, we want to obtain a dynamical system, a dynamical description for the evolution of the clusters. And then we want to show that this dynamical system eventually leads to the collapse and the formation of a single cluster. Okay. So if you like, this is a typical example of coarse graining, as we would call it in statistical physics. So we have a very high dimensional system described by n agents, and we want to describe a reduced description that involves only the evolution of the clusters. That is much lower dimensional. Okay. Maybe yeah, so I can summarize what we have. So as I mentioned, so if the interaction kernel has negative Fourier modes, and if it is attractive and sufficiently localized, so again, just think of the Hagselmann-Krause kernel, then we will definitely have the formation of clusters and a discontinuous phase transition, the formation of clusters, and eventually the convergence to a unique cluster, single cluster. We can compute how long it will take for the clusters to form. We can compute the number of clusters, and from this we can obtain a dynamical system for the evolution of the clusters that is of the form of coalescing Brownian motions. So what happens, and maybe I go back to my movie, sorry. Where am I? Here. Yeah. So what happens here is if I run my movie again. So when the clusters form, they start performing Brownian motions. So these are just pure Brownian motions, but with the additional feature that they can merge. So if they meet each other, so when they meet here, for example, then a new sorry, we got interrupted. So when the two Brownian motions describing the clusters meet, then a new Brownian motion emerges that has the variance that is the sum of the variances of the two motions that merged. Okay, so this is the mechanism. So let me go back. Okay, so and then you can you can show the so the fact that clusters form and then they interact and so on, also by solving the partial differential equation. And also you can study the effect of noise. There are lots of things that maybe I shouldn't get into, but yeah, so here's, if you look at the evolution of the densities, this is the sort of thing that you see. So you see several clusters that form, okay, and then eventually they will merge and form the unique cluster. Maybe just as an aside, and maybe if you like this kind of an amusing connection. So this sort of type of interaction, so local attractive interaction, and this type of conclusion that you have formation of clusters that then they interact and so on, was also, of course, observed in the physics literature in connection to some very simple models in stellar dynamics and things like this. So there's a nice paper from, well, 35 years ago, where they look at related models, and then, so here's their cluster. So if you look at this paper, so they used like a supercomputer in order to perform these numerical experiments, and then you could have access to the movie that they produced by asking them to send you the videotape. So things have changed in the last 35 years. In fact, they did. So this was done in Vienna, and then the Austrian Academy of Sciences, so he has made these videos available. So I should have showed. I mean, they sent them to us, which is very kind of them. But anyway, so this is the kind of cluster that you form here, and then this was interpreted to mean that this is kind of a sort of a galaxy forming and so on. But anyway, so this. Yeah, I think it's interesting. Okay, so I repeat, then we can compute the number of clusters. We can compute the time it takes for the clusters to form. And by doing this, we can obtain a very simple system model for the dynamics of the clusters. They're pure Brownian motions, but with and then we can compute the variances or masses of the clusters. And if we run then the reduced model that is consists of this kind of coalescing Brownian motions, and then we compute the statistics of the clusters, then the agreement is excellent. So here we have the full simulation of the n-particle system, and here we just run the clusters, I mean the Brownian motions, the coalescing Brownian motions, and you can see that the number of clusters can be predicted exactly. So we use the interaction energy as an order parameter. I can tell you a bit more about this. Okay, so there are lots of things that still need to be understood here, and in fact there are two mechanisms. So one is this noise-induced dynamical metastability that can be described using the so-called theory of large deviations. There is also slow motion for gradient flows that is a sort of deterministic phenomenon, and for which quite a bit of theory has been developed. So how much time do I have? Like 15 minutes or less? Okay, I will assume. Okay, thanks. Okay, so then we can describe. So there's a reduced system for the dynamics of the clusters, and we can compute all the interesting quantities like when clusters form and for how long they persist and stuff like this by using our reduced model. And again, I repeat the comparison between like solving the full dynamics, either at the level of the interacting particle system or of the corresponding Fokker-Planck equation, and by simulating the system of Brownian motions for the evolution of the clusters is actually very good. Okay, so now I will not. Let me skip this. So then the next two things that I want to mention very briefly are first how to learn parameters in this type of models from data, and second, how to control the dynamics. So I will provide a very brief overview of inference methodologies for interacting particle systems. And just to motivate this, so in addition to like models in the social sciences and so on, naturally, there are many agent-based models or interacting particle system type models that appear in finance. if you're interested, you can have a look at this very nice article by Giesecke, Schwenkler, and Justin Siriano, where they show several models of interacting agents that describe like interbank lending or systemic risk and so on. So the methodologies that I will briefly describe in the next like 5 minutes can be used very efficiently in order to infer parameters for this type of models. Now, for those of you who know a bit about like mean field games and stuff like this, so in many models for like, well, large financial systems, as they call them here, one crucial modeling feature is common noise, okay? And this is something that needs to be taken into account. So in the methodologies that I will describe, we do not directly account for common noise. This is an interesting question. Okay, so then I describe this first in a very abstract setting. So I take this mean field SD, so this McKin SD, so the drift here that I want to infer from data and that I parameterize in terms of parameters theta depends on the solution to my diffusion process and also depends on the law of the process. So it's a nonlinear diffusion process in the sense of McKin. And now for the measurement model, and this is crucial. So what I really need to be very careful is to describe what the observation model is. And there are different observation models that one can consider. So here I have a list of some of them. So first to observe n paths of the interacting particle system, but this n can be very small. In fact, in most of the papers that I've written on this topic, I have insisted that we only observe a single particle, discrete observations, discrete low frequency observations of a single particle. You can make your life much easier by assuming that you're observing paths of the actual mean field SD, but to my opinion, to my mind, this is completely unrealistic. Or you can assume that you're actually also observing the law of the process, but then this makes things too easy. So we don't want to do this, and it's not realistic. Okay, so there are lots of different inference methodologies. You might have heard about maximum likelihood. Maximum likelihood applies to this problem. You can prove rigorously that given this type of data, so paths like trajectories of the interacting particle system, you can infer parameters in theta using maximum likelihood. I'll skip all the details. You can prove rigorously that the maximum likelihood estimator is consistent, and also that it is so it's asymptotically unbiased, and it's also asymptotically normal. Okay, so you can prove a law of large numbers and a central limit theorem for this type of for the maximum likelihood estimator. Okay, I skip this. You can also do what we refer to as online parameter estimation. So you improve your estimator as you keep adding data. Okay, so this is like this so-called stochastic gradient descent algorithm, stochastic gradient descent in continuous time. Gamma t is the learning rate. So we apply stochastic gradient descent. So we think of the parameters that we want to learn from data as a dynamical process, and we write this stochastic gradient descent algorithm that we then want to prove that in the appropriate asymptotic limit actually converges to the true values of the estimator. This works very well, and actually also it works very well in practice, so it's a very good method to use. We can implement it and I'll just show some numerical experiments for the opinion dynamics model. So naturally, if this kind of bounded confidence models are to be used for any kind of realistic applications, they have to be calibrated using data. And this is not a problem at all. So stochastic gradient descent in continuous time, for example, applies very well. So we can learn we can infer, so for example, the influence radius from data, which is the crucial quantity of interest. My own sort of worry, if you like, about this is the lack of nice data sets that one could use. But rather than the lack of methodology, because there are lots of different methodologies that can be applied for this kind of inference problem. Okay, so this works actually very well, and it also works for models where so-called heterophilous models, where you can allow also interaction between sort of different groups of agents in opinion space. So when you have heterophilous dynamics. Okay, you can use spectral methods, so you can learn the eigenvalues and eigenfunctions of the Fokker-Planck operator corresponding to the interacting particle system and its mean field limit, and then from the eigenvalues and the eigenfunctions of the generator, you can infer the parameters in the model, and you can prove everything rigorously. And there's a lot of nice kind of functional analysis spectral theory involved in this type of estimates. Rather than telling you anything about the actual details, I'll show you some experiments. So this is a very simple model actually for systemic risk. So what we study here is this model for systemic risk that was introduced, was written down here. So it's this example 2.5. So now, whether this is a good model for systemic risk and so on, it's a separate question. But using data, and in particular, a single trajectory. So we only need to observe a single agent, and we want to learn the parameters in this function f, and we want to learn the interaction strength. The interaction strength will determine actually whether we have a phase transition for this problem, and then the disorder order phase transition for this type of models for systemic risk is the sort of the phase transition from solvency to default. Okay. Assuming that these models are correct, but I'm not getting into this. Okay, so then we can do this. So we can estimate the parameters in this model, and if we again we observe a single trajectory, but we need the number of agents in the system to be relatively large, so say 250, so that the proposed method is accurate. And we can also do this, as I mentioned, in the case where we have phase transitions, and the way the method works there, so this is below the phase transition, this is above the phase transition, is that first we learn the stationary state that we are at, and then we perform this eigenfunction expansion, eigenvalue eigenfunction expansion at the correct stationary state. Again, I'm happy to tell you details about this. This was joint work with Andrea Zanoni, who was a former PhD student. Okay. Okay, now I'll skip this. Again, you can do maximum likelihood, as I mentioned. You can use the method of moments. This works very well. You can do things in a fully parametric, non-parametric framework. So you can assume that you're actually observing, you have measurements of the solution to the nonlinear, to the Makin-Vlasov PD, noisy measurements of the solution to the Makin-Vlasov PD. And then you set up the inference problem as a Bayesian inverse problem. So you say that given these observations, you want to learn the interaction kernel as a function by setting it up, again, as I mentioned, as a sort of a Bayesian inverse problem. So you have a prior, a Gaussian prior for W, and then you want to show posterior consistency and so on. And this is joint work with Coley and Rai, who is a colleague of mine here at Imperial, and Richard Nicol, who is in Cambridge. Okay, we can prove that it is indeed the case that we can do this. I'm happy to tell you more about the details, but the point is precisely this. So there is a map, this so-called forward map, from the interaction kernel that we want to learn to the solution of the Makin-Vlasov PD, and then there is the inverse map from the solution to the Makin-Vlasov PD to the interaction kernel. Okay, and we need estimates on both the forward map and its inverse. We said we put a Gaussian prior, and then we use maximum likelihood and so on. Okay, I won't bother you with this. This is actually can get very technical, but we can prove rigorously that the method actually works, in the sense that as the number of observation goes to infinity, you can indeed learn the interaction kernel, and you even have optimal rates. So you can estimate how quickly the estimator, this posterior, converges to the true value. The last thing that I will tell you very briefly is how to actually steer the dynamics towards desired state. And this is joint work with Sarah Biseko, who was a PhD student here at Imperial, and Dante Calise, who is a colleague of mine here. So now the setting is the following. So again, if you think of, and I will go straight to the numerics. If you can think of this bounded confidence model, Hagselmann-Krause model, and you can think of it of variants of it in 2 dimensions. So for example, when you ask agents for their opinion about 2 different issues, like, you know, one can be, I don't know, gun control, and then the other can be whatever, some other issue. So you ask, so it's a 2-dimensional version of this Hagselmann-Krause model. Now, what we do then is, on one hand, we can identify all steady states of the dynamics, all possible configurations, so both disordered and ordered ones, and then choosing which one we're interested in or which one we prefer. We can use optimal control strategies in order to steer the dynamics towards a particular steady state. Okay. Now, in this paper, we do both. Like, again, if we sort of continue thinking about this model for opinion dynamics, we can, if we sort of identify the steady state of the system, the stable steady state, and it is the uniform one, so the one where no consensus occurs, then we can steer the dynamics towards the one that, the localized one that corresponds to consensus, or we can do the opposite. So if for whatever reason we're not interested in the dynamics reaching consensus, we can steer the dynamics towards the disordered state. Yeah, again, there are lots of things that can be done here. So for example, you can also steer the dynamics towards a particular clustered state corresponding again to polarization and so on. I can tell you more about this if you're interested in. And also, as I mentioned, you can use tools from machine learning and so on in order to develop inference methodologies. I sort of I advertise here a few papers where we do this, and I think I will stop here. Thank you.
Thank you, Professor, for the wonderful lecture. We're so lucky to learn from you today. We're going to move into the question and answer portion of today's event. So everyone joining us online, please put your questions in the Q&A section, which is just at the top of your screen there. And like any of the questions that appear that you want to be answered, and we'll try to get to as many of them as we can today. Okay, our first question today is from Robert. If you start with a single stable cluster, how would you induce a phase transition in the other direction from ordered to disordered?
Okay, yeah, this is an excellent question. Let's see how I can, yeah, okay. So what we would do then is that, so we start with a single clustered state, and we are in the regime where this is a stable configuration. So basically, if you like, we have already reached consensus. So the point is that we add an appropriate forcing term, like a control, to the dynamics in such a way that it steers the interacting particle system to the unstable steady state. So we are in the regime where, again, as I mentioned, we have identified all both stable and unstable steady states. And maybe actually let me share my screen, so because we have some details of this. Yeah, so maybe let me go back. Where should I go? Yeah. So one issue is to identify all stable and unstable steady states, and then we set it up as an optimal control problem. Okay. So rho infinity is the desired steady state, and psi here is the control. So And then, so we would substitute here, if you like, the disordered state, so corresponding to the uniform distribution. And then we need to solve this optimal control problem, and we do it via this Pontryagin maximum principle. Now, one important observation, and maybe this is actually the what the actual question was, that here we do this at the level of the PDE, so we don't actually apply the controls to the actual interacting particle system or to the agent-based model. This is the next thing to do. But the actual computation of the optimal control that can steer towards the disordered state is by solving this optimal control problem. I hope this answered the question, but I'm happy to give more details if needed.
Yeah, that's great. Thank you very much. We have another question from Alita. Can you share a little bit about your journey and what led you to pursue this particular field?
Yes, I would be happy to do this. So as I mentioned, so my background is in mathematical physics. So my first degree was in physics. Then I did a master's in applied mathematics, and then my PhD was in mathematics, in fact, on partial differential equations that are not too dissimilar from the kind of PDs that I showed here. So I'm kind of interested in all of the above. So I'm interested in like rigorous mathematical physics, again, along the lines of what I saw today. So like proving rigorously that you have phase transitions and so on. I'm very much interested in ideas from optimal control, also learning parameters from data. So inference, statistical inference is something that I'm very much interested in. And I'm also very much interested in politics and history. So again, I do not make the claim that the very simple models that I presented today have really anything to do with actual politics and history. But one of the reasons why, for example, for this last project that I showed on stabilization and so on, one of the motivations was precisely to see whether for this kind of very simple models for consensus formation, whether ideas from optimal control can be applied. So what drives me is curiosity. So that's yeah.
Thank you very much. Our next question is from Syed. What was an aha or eureka moment for you? Did you have more than one, and how did it affect you and your work?
That's a very interesting question. So most of like for the projects that I'm working on, usually it's a kind of a continuous time process that takes many years in development. So what I presented today, of course, I presented very briefly many papers. So it's work that has been done over a period of several years. So in some sense, there's kind of a continuous development and so on. But in this particular context, a eureka moment was this characterization of continuous and discontinuous phase transitions. So this was something that was kind of unexpected. Another kind of eureka moment in what I presented today was again, this statistical methodology that I very briefly described on computing eigenvalues, eigenfunctions of the Fokker-Planck operator, and then showing how they can be used in order to do statistical inference. Again, when we put everything together, I was very pleased with how well it worked, and yeah, I'm not quite sure whether I would describe this as a eureka moment. Yeah, but for me, as I mentioned, so I kind of think about all these problems all the time, and there's a continuous process of many small successes, maybe some failures, and so on. But and maybe just to tell you a story. So like when Heisenberg, one of the founders of quantum mechanics, he realized that his matrix approach to quantum mechanics, so what he referred to as matrix mechanics, was actually working. And then he knew that, of course, this was going to lead to the Nobel Prize and so on. So he was at a small island, like in the Baltic Sea, so like in sort of northern Germany. And then he couldn't. I mean, when he realized that he had made this huge discovery, then he couldn't sleep, and he was. I mean, there is a very nice. I mean, you can read about this online, so it's quite well documented. And if sort of this is what you think when you use the term eureka moment. Yeah, I'm not quite sure. I mean, for me, as I mentioned, it's kind of a continuous time process of like learning more about these things and developing them further. Yeah.
Thank you so much. We have a second question from Robert. In these models, do all of the agents have to have the same interaction strength?
Excellent question. No, they don't. So in fact, I mentioned very briefly dynamics on networks and graphs and so on. And this is towards the direction of sort of not all agents having the same interaction strength. What you're asking actually is a very deep it's a very deep question, because for this very well developed theory of interacting particle systems, how to pass to the mean field limit, so this is the technical term is propagation of chaos. A crucial assumption is that all particles are the same. So this is the so-called extensability assumption. So which means that if you take the law of the n particle system and then you permute two arbitrary particles, the law does not change. Breaking this and then being able to show similar results when not all particles are the same was only accomplished quite recently, in fact. So it was kind of a breakthrough in this business. But it's certainly the case that now we have the tools so that we can allow for different types of particles, different interaction strengths, and so on. Again, if you're interested, I can send you some references. So please do send me an email, and I can send you some references.
Thank you very much. We have a question from Grace. Can you see these models being applied in other fields in the future, such as economics and game theory?
Yeah, that's a great question. So yeah, so there is this theory of mean field games that was developed by Pierre-Louis Lyons, who is a Fields medalist. And in fact, he was interested in models in macroeconomics. And as far as I know, these models are used for several applications to macroeconomics, including systemic risk, which is one of the standard examples. So again, so if you add, in the sense, you have the agents that interact via some interaction law, and then they also try to sort of maximize profit, if you like, or they also have some sort of a game theoretic aspect to it. You can put things together, and then there's this very nice and very well developed theory of mean field games. Okay, so, and this is also very much related to evolutionary game theory. So it's certainly the case that these models can be and have been used in connection to economics and game theory.
Thank you so much. We have a comment question hybrid here from Syed. He says, when you mentioned politics and history, I was instantly reminded of Isaac Asimov's Foundation series and its concept of psychohistory and how this can maybe be related. And he's kind of like posing this as a half question. And he says he's currently watching season 3 of the TV show adaptation.
Yes, I mean, when I was a teenager, I read all the Foundation books, and I'm still a very big fan of them. The link between this kind of optimal control and sort of agent-based models and so on, and Asimov's theory of psychohistory has been made several times. So for kind of, I guess, people who like science fiction and who have read the books and so on, the analogy is quite natural, if you like. So in fact, with my friend and collaborator Dante Calisse, when we started developing this project on optimal control for agent-based models, Asimov's Foundation trilogy was mentioned many, many times between us. So yeah, so well spotted. Yeah, certainly. So there's a, it's one of the, yeah, so the analogy and sort of the connection between this type of mathematical models and Asimov's theory of psychohistory is quite natural, in my opinion. Again, just to add one comment to this. So I do not make any claims. I reiterate this, and maybe it's the third or fourth time I'm saying this. I do not make any claims that these models for opinion formation and so on can explain anything, right? So just to make sure. There are a lot of mathematical models that have been used in the social sciences, also in history, in fact. There are very detailed, specific agent-based models that try to explain the collapse of ancient civilizations, or they think of, they try to understand the sort of transitions between whatever, say, the fall of the Berlin Wall, whatever, in terms of tipping points. There is a vast literature on these topics, but I do not make any claims that. About the validity of these models. Okay, just to make sure that there's no misunderstanding there.
Thank you so much. That's the end of the questions from the audience. I have kind of one parting question for you. We're wondering if there's one thing you hope that the audience takes home with them today, what would that be? What would you like them to remember?
Okay, very good. Yeah, so I think maybe if you allow me, I would say two things. First, that there is this very nice interplay between many different areas of mathematics that can be useful in different contexts. So there is, if you like, a new kind of paradigm. We like to use the term of Thomas Kuhn in modern applied mathematics, where we use rigorous mathematical analysis, statistics, machine learning, optimal control, and this is something that I very much believe in, and I think this might be a very good way of kind of trying to do this kind of applied mathematics. So in terms of methodology, if you like, I think this might be a useful take-home assets, if you like, that one does not have to be. I mean, it's important in order to study modern problems and modern challenges and so on, using mathematical tools, for someone to be versatile and to sort of be able to use lots of different tools. And the second thing is that I think this idea of like using mathematical models in order to study problems in the social sciences, and I include in their economics, of course, is something that is very exciting. It's very exciting, and I hope that maybe some members of the audience will find it interesting. But we need data. So for all these models to be of interest to practitioners, or for people who try to understand phenomena in the social sciences and so on, they have to be calibrated using data. Okay, so maybe these are the two take-home messages.
Amazing. Thank you very much. On behalf of everyone that joined today, I just want to say thank you, Professor Pavliotis. It was wonderful getting to hear about your research into multi-agent systems and some of their applications. And thank you, everyone that joined us online. We're very grateful that you come back and join these lectures. This lecture will be posted eventually on ATCO's YouTube channel, so if you want to watch the replay or share it with anybody, feel free to do so. I'll let you all go and enjoy the rest of your day. Thank you very much.
Thank you so much. Thank you. I really enjoyed it. So thank you very much for the invitation. This was great.